Denis, je t'invite à présenter Saed.
Oui, bonjour. Bienvenue à tout le monde au séminaire de Saed Moradi. Saed travaille avec moi comme postdoc sur la segmentation d'images 3D et l'extraction de primitives géométriques, principalement des cylindres, pour une application de robotique. Donc, je vais le laisser présenter son séminaire. Welcome everyone. To this seminar that will be given by Saed Moradi, who is a postdoc working with me on the detection and extraction of geometric primitives, more precisely cylinders, in 3D images for a robotics application. Saed?
Hello everyone, I'm Saed and today I'm going to talk about multiple cylinder extraction from organized point clouds. But before going into detail of our algorithm, let's have some definition. The first word is an unorganized point cloud or simply point cloud. A point cloud is an unordered set of 3D data points. It's a set, so the order of the point doesn't matter in the representing of this type of data. On the other hand, we have an organized point cloud, which each component of the 3D data X, Y, Z is stored in a 2D grid. So each component is just like a gray image. And for cylinder detection, we are trying to finding all points belonging to the cylinder surfaces. And for cylinder extraction, we are trying to identify the axis orientation, a point on the axis, and the radius of the cylinder. Okay, let's take a look why we interested in the detecting and extracting the cylinders. The most objects in the real world are composed of a geometric primitives, which are a simple shape, just like cube, cylinder, sphere, plane, and so on. All the complex shape can be made by combining these simple shapes, and among these primitives, cylinders are the most frequently used in the real world scene, and that's why we are interested in the detecting and extracting the cylinder. Okay, this is the block diagram of our method for extracting the cylinder from an organized point cloud or a depth map. The red blocks shows the operation has been applied to the data, and the black box shows the data, which is the input of each step. All proposed method consists of the 3 steps. The first step is a normal estimation, which is, our method is fast and accurate. The second one is to detect the cylindrical region from the input data, which is, I will tell you, we call it theta image. I will tell you in the following how to acquire this image. And the final step is to extract the model of each cylinder from the detected regions. So let's go for the normal estimation. The common way for estimating the normal from unorganized point cloud is to identify the neighborhood of a query point, and after identifying the neighboring point, fit a plane to those points, and when the plane is fitted, the normal vector to that plane can be easily achieved. This normal vector can be considered as a normal vector to the first query point. And for calculating this normal estimation, at the first step, a covariance scattering matrix named C should be constructed using this formula. And by eigen decomposition of this matrix, the eigenvector corresponding to the smallest eigenvalue is the normal vector for that query point. This method is accurate enough, but since it's work on an unorganized point cloud, and which is, there's an extra step for identifying the neighborhood, constructing the scattering matrix, and eigen decomposition. It has a high computational complexity. So we go for the normal estimation directly from the depth image, because in the depth image, we don't need to identify the neighboring points for a query point. So this step, it's canceled for our method. And for the processing the image, we can use the 2D image operator, which are fast enough to be used in the practical application. And the main concept to estimate the normal vector from a depth image is to choose a two tangent vector and find the cross product of these two vectors, and the resulting cross product is a normal vector for that point. There are some methods in the literature which well known in this area and highly cited. So we use this method as a baseline algorithm to compare our method with these methods. Okay, the first one is a Tang method. As the other methods, the normal vector is the result of cross product of a two tangent vector, Sx and Sy. The problem with this method is that they construct the tangent vector from the first step in a wrong way. So the final normal vector is not what it should be. The second method, which is already implemented in the point cloud library, the point cloud library is a C++ based library to accelerate 3D operation. This method, the Holzer method, is implemented in PCL, another method we used for the comparison. As the previous method, they also use the cross product, and this is the different component of a vertical and horizontal tangent vector. They use the integral image to speed up the operations, because using a single vector to calculate the normal vector result the wrong result when the point cloud is noisy and the quality of the scanner or the acquiring device is poor. Okay. The third method proposed by Nakagawa, they also use the same approach, but the problem with their method is that they, at the first step, they used this approximation for the partial derivative. The approximation propagate until the end and result a low quality normal estimation. But for our method, we use two tangent vector SH and SV, and unlike the other methods, the length of our vector is not it's not a unique vector. The length of each vector is equal to alpha. So we find a closed form solution for the different component of a normal vector using this formula. So actually our method has one step less than the other method. At the end of it, all those methods they have to calculate the cross product of a two vector, which in our method we do not need that step because we have a closed form solution for the final normal vector. Okay, let's see the result. Before talking about the result, since the normal vector are a three-dimensional component, we can just easily compare the different algorithms. So there are two ways to compare the different methods. The first one is that for an organized point cloud, you can consider each component as a color channel for an RGB image. So the final normal vector can be represented as a color image, and we can compare those methods. The second method is to convert the Cartesian coordinate into the polar coordinate. Since the third coordinate, which is the radius, is a unit vector and have no useful information, we can just compare the phi and theta component of the normal vector for the quality comparison. Here we use the second method. The first row is the phi image and the second row is the theta image. The first column is a ground truth, second column is our method result, and TM, HM, and NM stand for Tang's method, Holzer method, and Nakagawa method. As shown in this figure, our method has the best match with the ground truth. We can use some image similarity metrics just like SSIM and so on, but Here I just brought the visual comparison of a different method as shown in this figure, or method outperforms the other baseline method. So this is for our first step. And also just let's take a look at the execution time of a different algorithm. The first row is a scattering matrix-based method, which applies on unorganized point cloud. It took almost 6 seconds to finish the normal estimation procedure. The other method, the Tang's method, is the fastest, but as shown in this figure, it has the bad quality for the normal estimation. Neglecting the Tang's method, our method is the fastest method among these 3 methods. Okay, let's go for the cylinder detection part. There are two different ways to detect the cylindrical region in an depth image. The first one is using the radial-based surface descriptor, or RSD, and the second one is used to use a principal curvature. What we use, since the cylindrical areas in a theta image are sharp enough to can be detected using a normal region detector method, we used MSER feature descriptor to extract or to detect a cylinder and extract the cylindrical regions. So this is the result of a cylinder detection method. The first column is a ground truth. The second column is our method, which is based on MSER feature descriptor. Third and fourth column is the RSD and principal curvatures result. As shown again, our method can detect all the cylinder correctly. Okay, the last part is extracting the cylinder. By extracting, we have the orientation axis, the radius, and a point on the orientation axis. So by having these 3 parameters, we can create a CAD model to replace the points in the point cloud with that CAD model to simplify our process. The well-known method for the cylinder extraction are the ransack method and another method which is done in our lab under Professor Lorando's supervision, done by Tiens, and the paper is published on Computers and Graphics on 2014. What the first step of the extracting the cylinder is to find the orientation axis of the cylinder. After finding the orientation axis, we can project all the points along that orientation axis, and the extraction problem is relaxed into a simpler, just a simple circle fitting. And if we can find the center and the radius of that circle, all the 3 parameters of the cylinder are revealed. Okay, this is our cylinder axis orientation, our proposed method for identifying the cylinder axis orientation. From the last step, we detected the different patch of which belongs to the cylindrical regions. We took them as the input for this algorithm. We rotate the region to achieve a vertical cylinder patch, use a morphological dilation to fill holes and have a somehow perfect square patch. By finding the bounding box and choosing 2 points in the middle of the vertical line, we can find the orientation axis of the cylinder. And after finding the orientation axis, we can project all the points on the 2D plane and fit a circle to those planes and find the center and the radius of the cylinder or the circle. Okay, this is the last result of our algorithm. The first column is the RGB image of the scene. The second one is the depth image acquired by the same sensor with the Kinect Azure. Both RGB and depth image are acquired with the Kinect Azure. The detection step is shown in the third column. The green ellipse are the detected cylinders. And finally, the extracted cylinders are colored with a CAD model in the 3D scene. And these are the references I used for this presentation. And if you have any question, I will for you.
Okay, thank you, Saed. Any questions? Well, I have one.
Okay.
We discuss every Monday morning, but I have a question. In the scenes that you have shown, at least the 2-point clouds in the last slide, this slide,
okay,
the cylinders are mostly vertical or horizontal. Would there be any problems if they were oblique or tilted in the image, but not perfectly vertical or perfectly horizontal?
I don't think so, because I have more results
okay.
on the paper, because there wasn't enough room for the images. I just brought 2 of them.
You hide things from me. Okay, so you answer my question. Any other questions? Or in the chat? I don't see the chat.
Actually, there's a question from Stéphane Guinard. Stéphane, est-ce que tu voulais poser ta question?
Yes. So thank you very much for your presentation, Saed. It was really clear. I really appreciate that. And actually, I'm working on a similar problem of yours, but I'm working with LiDAR data and geometrically simplifying LiDAR data using geometric primitives. And so I'm trying to build bridges between both our works. And I would have 2 quick questions. My first question will be, what is, do you have an idea or an estimation of a geometric precision of a cylinder you extracted compared to the original data? Are they close? Are they far? And what is an acceptable result in your case? And my second question will be, are you robust to occlusions, to missing data? Ideally, how many points do you need to find a cylinder? Are 6 points enough or not? Because mathematically, 6 points should be enough, but is it the case for your method or not?
Okay, let me just answer your second question first, because the camera we use to acquire the data is a high quality 3D sensor. 3D sensor is a Kinect Azure, so it has a dense point cloud. I'm not sure about the sparse 3D data, how our algorithm will work on the sparse data. I didn't test that, so I'm not sure about. I will test it, and we can be in contact to share our idea and experiences. And for the first one, I forgot the first one. Please ask it again.
Yeah, no worries. My first question was about the geometric precision of the cylinders extracted compared to the original data.
Okay. You think that is there any ground truth that I compare my method with that to find the accuracy of my method, right?
Yes.
Okay. We are working on that. To do so, because when you acquire a real data, you don't have a ground truth. You have to somehow build a ground truth for that. For this type of data, we can't do that easily. So the alternative approach is to build a CAD model and somehow simulate a sensor to create a depth image from that scene, right? The scene that all the parameters for the cylinders are known, the orientation axis, the cylinder, and all the points. So in that case, we can measure the accuracy of our method. But now, without any ground truth, I can't tell anything about the accuracy of the method. But for the first step, which is the orientation axis detection, I compared my method with a TN method, which is a highly cited method in the cylinder extraction. We extracted almost very similar orientation axis for each cylinder.
Stéphane, out of curiosity, are you working with Philippe Giguère?
No, I'm working with Thierry Badard and Sylvie Daniel.
Oh, yeah, okay. So it's they are good friends of mine. So I was just curious because Philippe Giguère is working on the extraction of trees from LiDAR data, and of course trees can be assimilated to cylinders. So that's why when you asked your question, I was curious about whom you were working with. Any other questions? I have another one, Saed. We've discussed the computational efficiency of the normal computation step,
Okay.
but do you have an idea of the overall cylinder extraction computational complexity for all the steps? How long does it take to detect this?
No, I didn't measure that. I will measure it and report it to you soon.
Okay. Okay, so we still have discussions to
Yes.
have next Monday. Okay, any other questions? D'autres questions?
Yes, I will have a question.
Yes.
I will just put in my camera. So do you need the entire point cloud of the object you are trying to find the cylinder? Like if you just have your sensor in front of the cylinder, can you just have like half of it to find its shape?
Actually, we don't have a full 3D data since we just using a depth image. We have a 2.5 data, you know, or
Okay.
2.5 data. So in the best case, we just have a 40 or 50% of the data of the cylinder surrounding points. So that's not a full data. It's a partial.
Yeah.
After projecting the data, it's a partial circle.
But do you think that if you will have the entire thing, it will work even better? Yeah.
I don't think that there will be any difference between them because the cylinder fitting method are rich, and you can they work from the small part of the circle or the onto to the full circle of the data, you know.
Okay. And did you, in that case, did you try to use half of the shape of a cylinder to fit it with the?
Actually, I told that all my cylinder are half. You know, if let me just show this one. You know, this is the image. It is taken in front of the scene. So, for example, do you see my mouse cursor here?
Yes, I see.
Okay.
Yeah.
For example, for this one, at the best case, it's just 30% of the surrounding point of a cylinder. You know, it's not a full point of the. So after projecting, it's still a 30% of the whole circle. There's no problem to fitting a circle to those points.
Okay, thank you.
Maybe a complementary answer, Vincent. Tien's method, actually, when Tien's worked on segmentation of primitives out of point clouds, he was interested in detecting circles, no, not circles, spheres and cylinders. And in his framework, he converted the problem of detecting spheres and cylinders into one of detecting circles. And since there are many circle fitting algorithms in the literature that are very robust, Tobin's method is one of the most popular, then everything he wanted to detect was limited to the detection of a circle. So that we adopted a similar strategy, which is interesting because no matter what the primitive you want to detect finally ends up in the detection of a circle. And it worked pretty well. I'm pretty much convinced that the more points you have on the circle, the best the circle fitting will be. But Tien has shown that the algorithms that are currently available for circle fitting are quite robust to noise and outliers.
Okay, thank you, Denis. And Saed.
Welcome.
Any other questions? Okay, so if we don't have any other questions, if we have a cylinder to detect, then contact Saed directly. Okay, otherwise, thank you very much, Saed, and thank you for the participants. And Annette, I think you want to announce that there will be one more seminar in this summer.
Yes, there will be another CeRVIM webinar given by Mohamed Baradaran, who's present today. And it will be on deep learning-based semi-supervised video anomaly detection methods. So that will be this coming Monday, same time, 11 o'clock.
Okay, bien, merci tout le monde. Thank you very much, and have a nice weekend. If there are no news, no additional news to announce.
Yes, thank you, everyone. And thank you very much, Saed, for your presentation.